Good morning. Okay, welcome to the class today. So, can you hear me?
Yes.
Good morning.
Good morning. Yes. Okay. So, welcome to the class today. So, in today's lecture, we will be discussing about the second part of uh, the previous topic. That was about the bracketing method. Okay, so in the bracketing method, the first method is the bisection method. Previously, we discussed about the graphical method, but of course, graphical method is quite general. So in the uh, bisection method, the process is as follows. So first of all, we have a function, and we represent the function in the form of f of x is equal to 0. That means we make the function, we make the right hand side of the function as 0. So that means we bring all the values on the left hand side, all the variables on the left hand side, and then we make it in the form of an equation. Okay, f of x is equal to 0. Next, we determine two values of the independent variable x, xl and xu, such that for one of the such that the values of the function of x at xl and xu are of opposite sign. In other words, f of xl multiplied by f of xu will be less than 0. Less than 0 means it will be a negative number. Okay, so f of xl times f of xu will be less than 0. So once we determine that, this will give us an indication that there may be a root between f of xl. There will be a root between xl and xu. Considering that the function is a continuous function from xl to xu. And next step will be in this bisection method is that, as the name suggests that, so the bisection method then assumes that the solution will be halfway between xl and xu. However, that may not be that may be only an approximation. Okay, not the exact. So our objective will be to reduce this approximation to the permissible limit. So for doing this process, what you will do, you will find the average of xl and xu. That means bisection point of xl and x2 by xl plus xu divided by 2. And then you will determine the value of the function at this midpoint, value of this function at this midpoint. So now by doing this, we will have the value of the function at the midpoint and the value of the function at the endpoints. So earlier two endpoints were of the opposite sign. And then if there will be a midpoint, then that midpoint may be either a plus or minus. Okay. So in that case, there may be two situations that can arise, rather three situations. Okay. The first situation may be that if f of xl times f of this new point is less than 0, then that means xl and xl plus that midpoint xl and that midpoint xl plus xu over 2 is of the opposite sign. So it means that the root will next approximation of the root will be between xl and xl plus xu. So in that situation, the upper limit will become xl plus xu over 2. Okay, the new upper limit will become x. So we will increase the new upper limit. And then in this case, for the next approximation, we will go back to this point number 2, and then repeat the process. On the other hand, because here is this if statement. On the other hand, if uh, we have on the other hand, if we have just a minute. Yes. On the other hand, if in the second option, because we have this if statement, if this is then this, and if on the other hand, if f of x of L times f of xl plus xu over 2, that means that midpoint, their product is greater than 0. That means then both are of the same size. Then it will mean that f of xl plus xu over 2 and f of xu will be of the opposite sign. Then that means the root will lie between in the upper interval. Okay, that from this midpoint to the upper interval. So in that case, this point f x l plus xu over 2 will become the lower limit. So the upper limit will be as before. So we will go back to the step 2 and then we will repeat the process. So in this case, then we will keep on repeating the process. And the third situation can be that if f of that will be rare. If the third situation is that f of x of L times f of xl plus xu over 2 is equal to 0, that means exactly equal to 0. So then then actually xl plus xu over 2 is actually their root, and then we already find the solution, so we will terminate it. Anyway, but that situation is rare. Uh, in most of the cases, it will be either of these two previous situations. So until when we need to repeat the process. So for this purpose, we will compare the epsilon s with the epsilon a. What is epsilon s? Epsilon s is the stopping percentage error, and epsilon a is the approximate percentage error. So stopping percentage error is normally given. So and in the chapter number 3, we have also looked at the formula for that. That was about 0.5 times 10 to the power 2 minus n. Okay, the formula on page 61 of the textbook, equation number 3.7. Okay, 0.5 times 10 to the power 2 minus n, where n is the desired number of significant digits for which we need to find the correct answer. However, epsilon a is the approximate percentage error. So approximate percentage error we can find by this formula or by this formula. Okay, so this first formula is a general formula which is applicable to the bisection method as well as some other methods as well, the later on the false position method. Whereas this second formula is only for the bisection method. Okay, so you can for the bisection method we can use either of these two formula, but the advantage for the second formula is that you can even find the value of the percentage approximate error for the first approximation as well. But by using the first formula, we can only start the percentage approximate error only after the only at or after the second approximation, because in the first formula we need the new approximation. Okay, that is xr is the approximated root, new approximated root, and then we have to subtract it from the old approximated root. Okay, so however in the second formula we can just take the xu and xl, because we can start from xu and xl, and then we can determine this absolute error right from the first approximation. And then later on the value, either of the values of the XU and XL will be replaced either by if it is the, if it is for example the first case, then XU will be replaced with that XL and XU, uh, which is present at that position. And in the second case, XL will be replaced by XL plus XU over 2. Okay, so here I wanted to stress this point because you may find that in the solution sometimes we will maybe using this formula or this formula for the uh, percentage approximate error. Both formula in fact will provide you the, will give you the same result. Both formulas are equivalent to each other. Okay, but you should be aware of that. So this process will be repeated until the absolute percentage error is less than the percentage stopping error. And the percentage stopping error, as I told, that it is determined from equation number 3.7 of the textbook, page 61. I don't know, maybe of the textbook. Okay, so epsilon s is equal to 0.5 times 10 to the power 2 minus n, where n is the number of significant digits for which we need the accurate answer. Any explanation needed for up to now? Do you have any questions?
No, but in the book, is there like a derivation of the relative error formula that the second one
Yes, the
was?
derivation is there. I'm not going into the derivations in this course. The derivation of the second formula is there.
Okay, thank you.
Yeah. But remember that this second formula is only applicable to the bisection method. Okay. So don't
Okay,
use this second formula for any other method. Okay. The first formula is applicable to any method. Okay? So as a result of this visual expla to explain it this method to explain the bisection method visually, we can see that there is this curve, and that curve is this crossing this x-axis between points 12 and 16. So we can see that this solution will lie between 12 and 16. So we will bisect 12 and 16, and then our next lower term, and then we can see that 12 and 16, the bisection point is 14, 12 plus 16 is 14, but 14 is here. So in this case, 14 is here. So 14 is towards the left of the intersection point. So that means the next approximation will lie between 14 and 16. Okay, but now we further zoom in to this situation, and then we can see that after 14 there is 14.5, and then there is this 15. So the solution lies between 14.5 and 15. Okay, so here we can see that the solution lies between 14.5 and 15, but of course, because we can only change one of these values, so therefore we can say that this next approximation will be between 14 and 15 in this case. So in this way, that means this kind of method is kind of like zooming in or zeroing in to the uh, uh, exact solution. Okay. Okay, let's see the example 5.3. By using the bisection method, solve this same problem approached graphically as in example 5.1. So before you forget what was there in the example 5.1, So you can see that in the example 5.1, we solved graphically this equation for the value of C. And then for various values of C, we can find the values of the function. And here, from here, we can see that the value of C changes from, the value of this function changes from plus to minus, from the values of C from 12 to 16. So which will mean that uh, the root of this equation will lie between 12 and 16. So in the bisection method, then the first approximation will give the root as 12 plus 16 over 2 is equal to 14. So which will give a total percentage error of 5.3%. But here I think actually we did not calculate this total percentage error. So we suppose that we know the result. Okay, we suppose that we know the result of this equation. That means we know the exact answer of this equation to certain number of significant digits, and from there we can find the true percentage error. Okay, true percentage error. So therefore true percentage error is 5.3% in this case, which gives us uh, uh, normally you will find the absolute percentage error, but that we can do in some other examples. Okay, so in this example we can show it with the true percentage error. So the first approximation gives 14, and then we will calculate the value of the function at 14. Okay, and the value of the function at 14 is 1.611. So but now we can see that f12 was also plus, f16 was also plus sign, so both are in the plus sign. So it will mean that our next approximation will be between 14 and 16. Okay, because 16 it was negative, so the next approximation which will be between 14 and 16. So next R will be 14 plus 16 over 2, that will be 15. And for this 15, the true percentage error is now reduced to 1.3%. So as a next step, now we will calculate the value of the function at 15, which will be minus 0.384. So now since it is minus 0.384, so it will mean that the next approximation will be between 14 and 15. Okay, it will be 14 and 15, because at 14 it was plus value, at 15 it is a negative value. So it will be between 14 and 15. So XR is equal to 14 plus 15 over 2 is equal to 14.5%. And in this case, the true percentage error is 2%. Okay. So here you can see that you can keep on repeating this process until the true percentage error becomes lower and lower. But here you can see that the true percentage error has first decreased, and now in the third approximation it has increased a little bit. Okay, it has increased a little bit. So we will see this effect. I will illustrate this effect later on in a graphics form. Yeah, okay, just ignore it. This is just the repetition. Okay, next we have example 5.4. We continue this example 5.3 until the approximate error falls below a stopping criteria of 0.5%. Okay, so in this case, the stopping criteria is given as 0.5%. Normally 0.5% stopping criteria is for two significant digits, because if we use the formula for stopping criteria from equation 3.7, for the value of n two significant digits, we get this 0.5%. So in this case, we can use the absolute error like this. So the results of the first two iterations from, for example, 5.3 and were 14 and 15. So substituting these values into this equation, that means this equation. So we get a percentage error of, because in the first approximation we get 15, and in the second approximation we get, in the first approximation we get the 14, and in the second approximation we get the 15. So if we input, so therefore this is the old, this is the old error, old result, and this is the new result. So you can see that in this equation, new minus old over new. Okay, so new minus old over new. So that is the percentage approximate error. Okay, times 100, and then we are using the absolute values over here because we just want to see the magnitude of the error. The sign is not important at this point. So in this case, it is 6.667%. If we repeat this process, so for this solution, that means for the previous example, and then we will see that it will be 14.5 to 15, and then 14.75 to 15, 14.7 and 14.85, and then in this way we will get the absolute errors like that. Okay, so let me, yeah, this may be shown on the Microsoft Excel, maybe better. Yeah.
Excuse me, I have a question.
Yes.
How do we find true percentage error?
Yeah, the true percentage error is equal to the true value minus the approximate value, and then divided by the true value.
So we were given like the true value, right?
Yes, for some of these functions, we know the true value. So in this case, we actually are assuming that we know the true value. But
Okay.
for most practical situations, we will find the approximate value.
I also have a question.
Yes.
So basically, the bisection method allows us to find the root of the of the function. Yes.
Yes, this is for finding the root of the function.
But what if our function has like multiple roots?
We
Will
can
we be
also
able?
find, yeah, so for the multiple roots, we have to first plot the graph and then need to determine the approximate location of the multiple roots. This
Okay.
bisection method or many other methods, numerical methods, are not the exact methods. So they are like trial methods. So if there are multiple roots, so we first of all we must plot the graph and then try to find the approximate solution first, approximate location, and then we can further refine it by the bisection.
Okay. Thank you.
Okay. Yeah. So if we want to apply it in the in this, so I can take the value of the C and then the value of the function of C, function of C. Okay. So C and function of C. So if, for example, C is 12, and then let me calculate this function. So it is 668.06 divided by C, 668.06 divided by C, and multiplied by 1 minus exponent of minus 0.146843 times C. C is this, and that is the close, and then minus 40. Okay, and then this was not C actually. Yeah. So if it is like this, so then we get the value of 6.11. Is it correct? Yeah, 666.11. So, okay, so in this way, I have actually formulated that equation. So now I determine this function at say, I'm now trying to illustrate it on the Excel, how we can apply the bisection method. So on 16, so for 16, we can calculate this function as like, it will be minus 2.23. So now since both are of the opposite sign, our next value of C will be the average of, that means the half of 12 and 16. So it is average of 12 and 16 is equal to average of 12 and 16. Okay, so it will be this. So now we determine this value. So we get a value of 1.611. So now for this 14, now it is plus, and then for 16 it is minus, for 12 it is plus. So now the next root is between 16 and 14. Okay, so we get equal to average of 16 and 14. Okay, so it will be 15, right? And now the value of the function, we can determine it like this. So now in this case, now it is plus and minus, right? So it will be between 14 and 15. So it will be average of 14 and 15. So it is 14.5. So now the value is plus again. Okay, the value of plus again. I can take one more trial. Okay, and then average of 15 and 14.5. Average between 15 and 14.5. This is 14.75, and then maybe, but we have to stop somewhere. Okay, stop somewhere. So now it is, I think it's quite close to 0, this function C. So we have to stop somewhere. So for this, we can determine the epsilon A. So we can say epsilon A. Okay, epsilon A, percentage relative error. So what is the percentage relative error? Percentage relative error is equal to the x new minus xr, x old. Okay, so the first two values were actually given values. Okay, the first two values were actually given values. First approximated value was 14. Okay, and then the next approximated value was 15. So I think we can start epsilon A from here. Okay, so the new value was 15, and the old value was 14. Okay, so it is equal to the new value minus the old value divided by the new value, and then multiplied by the 100. Okay, so it is 6.667, and then you can see that it is now reducing. So it is 6.667, and then it become minus 3.8448, and then because we are to avoid this minus sign, we can take the absolute value. Okay, so absolute ABS, absolute value. Okay, so the absolute value will keep decreasing. Okay, from 6.667 to 3.44 to 1.69. So in this case, now actually what we can do is If I want to further reduce it, so now the average will be, now the next bisection will be between 4.75 and, can you tell me which point we should take for the next bisection? 14.75 and
15.
which, and
15.
15. Yeah, because it is
15.
at 14.575 it is plus, at 15 it is minus. So the next bisection will be like, or 14.75 plus 15 divided by 2, okay, or average of these two values. And now we can calculate this function. And now it is minus 14.75. And now if we calculate the epsilon A, so it will be 0.84. So you can see that epsilon A is continuously decreasing, okay, approximate percentage error, okay. You can calculate the epsilon t, that means the true percentage error, but of course that will be just similar to that. So for this, we need to first find the solution of this, and then we need to determine it. But let I leave it over.
Sorry, I have a question.
Yes.
Can you show Excel file again, please?
Yes.
So here, shouldn't we take for the seventh value not 14.75, but the average between, okay, sorry, I got
Yes,
it.
so we took 14.75 because it is the average of 15 and 14.5, because these two values are of opposite sign. And then the next value is, we took 14.875 because this new value, and then this was also of the opposite sign. So it was the average of 15 and 14.75. Clear now?
Yes, thank you.
Okay. So that was example for 5.3, and we already covered it. So here I think then you can repeat it. So you can see that we have gone up to 0.84, right? 6.67, 3.44, and in this Excel, yeah, we have gone up to 0.84. Okay, so the same information. So now this table is clear, and then now what we can see, that you can see the behavior. Here you can see that the behavior of the true percentage error is given by this blue line, and the behavior of the approximate percentage error is given by this black line. So you can see that the as the number of iterations are increased, the approximate error continuously decreases. However, there is a zigzag situation in the true percentage error. So after some in some initial stages, the true percentage error decreases and then increases a little bit, and then decreases and then increases a little bit. So so this is because of the mechanism of the bisection method, because in the bisection method each times we halve the interval, and sometimes when we halve the interval, then that that midpoint becomes relatively moves relatively far away from the true solution. Okay, so that's why there is this zigzag type of situation in the true percentage error. But on the other hand, approximate error continuously decreases. So errors of bisection method. So true and estimated errors are plotted versus the number of iterations. Okay, so for the evaluation of this method, that is the bisection method. So its benefits are that this is an easy method. We can always find the root. Okay, so this method does not fail you. So you can always find the root. And the number of iterations required to attain an absolute error can be computed a priori. That means beforehand we can determine the number of iterations required for the solution. There is a formula in the book, but I am not going into that formula or any application. So for this course, maybe you can just exclude that part. Next is there are some disadvantages of this method as well. Although it is an easy method, but it is a slow method. It needs more number of iterations usually to get to the desired level of solution. So we must know A and B that bound the root. Okay, so that means someone talked about the multiple roots. So we must, for each multiple root, we have their respective A and B bound values. Okay, and then this means that we must employ some other method first to determine the interval of A and B. And in the case of the multiple roots, we may not be very much sure that whether we can find all the roots or not. Okay, and then no account is taken of f of x of L and f of x of U. And if f of x of L is closer to 0, it is likely that the root is closer to L. Yeah, so since this method is quite rigid, every time it takes the half of the interval. But if you logically think that the root will be closer to that point where the f of closer to that point where that the value of the function will be lower. Okay, so for example, if the value of the function at one point is 2 and at another point is -1, so we may expect that the root will be closer to that value of xl for which the value of the function is -xl. So that in fact is the concept which is used in the next method, which is the method of the false position. So therefore, this is the false position method. In fact, this false position method is nothing new. Maybe you have used in some other situations as well. It is the kind of the which is the kind of the method which is called as the method of the similar triangles. So if a real root is bounded by xl and xu, then f of x is equal to 0, then we can approximate the solution by doing a linear interpolation between the points fxl, f of xl, and xu and f of xu to find the xr. The value is such that the L times xr is equal to 0, or L of x is the linear approximation of the f of x. Okay, so this picture illustrates this method better. Okay, so this method then assumes that, so for example, if x of L is equal to here the value of the function is negative, and here the value of the function is positive. So instead, in the bisection method, we will assume that the root will be between xl and xu. That means at the midpoint of that. But here it will take the linear approximation, and like just like a similar triangles. Okay, so you will take this small triangle and this bigger triangle, and then we will compare these the lengths of the sides of the triangle, and then you can find the unknown value of xr. So by simple algebra, you can find that the value of xr then can be found as like this. Xr will be equal to xl times fu minus xu times fl, fu minus fl. So the procedure starts like this. Find a pair of values for x, xl, and xu such that fl is equal to f of xl is less than 0, fu is equal to f of xu is greater than 0. Determine the value of the root from the following formula. So refer to this the box in the picture in the textbook. So in this case, you just have to remember this formula. Okay, so for example, if you want to find this xr, so you will take the lower bound x value and then multiply it by the upper bound value of the function. then you will take the upper bound x value, then we will multiply it by the lower bound value of the x function. And then you will subtract by the difference between the upper bound and the lower bound value of the function. So in this way, you can just try to memorize this formula. And then in this case, you can determine the x value of the xr, and then you will determine the f of xr. And then again, the new value of the x of xr, then if it is between these different points, then you can determine it. So use the new point to replace one of the original points, keeping the 2 points on the opposite sides of the x-axis. So if f of xr is less than 0, then x is equal to x1, xl is equal to xr, and then it means that fl is equal to f of xr. And if f of xr is greater than 0, then xu is equal to xr, and then fu is equal to f of xr. Well, in these symbolic forms, it is sometimes confusing. So although conceptually the method is very much straightforward. So let's see it with the help of example. Okay, so normally the method, the advantage of this method is that it is relatively faster, and it always converges for a single root. Okay, example 5.5. So we can use the same problem. So, but this time we will apply the false position method to determine the root of the same equation investigated in example 5.1. So as in example 5.3, initiate the computation with the guesses of xl is equal to 12 and xu is equal to 16. Okay, remember that this was the original equation and the data. So we know that at value 12, it is this, and at value of 16, the value of the function is minus 2.23. So we can apply this formula. Remember that this is not the formula that I just explained in the previous slide. This is another form of the same formula. Okay. So you can either apply any of these two formulas. So first of all, we will determine the value of the xr from xu and xl and xu. So what is xr? Xr is the approximated root. So approximated root will be equal to, in this case, approximated root will be equal to, in this case, equal to xu, that is the upper bound x value minus, now this is the value is the upper bound function value times the difference between xl and xu, and then the lower bound x of xl value minus the f of x u. Okay, and by applying this formula, so first we have xl is equal to 12 in this case, xu is equal to 16, f of xl is equal to 6.113 minus 2.23. So so you can try to memorize it. So for example, 16 is the upper bound value minus, and then this is the upper bound function value, and then times lower bound value, lower bound x value minus the upper bound x value, and divided by the lower bound function value minus the upper bound function value. So in this case, in this way, it will give an approximation of 14.309. Okay, 14.309. And remember that all these formulations can be very easily derived by considering the similar triangles. Okay, according to the figure which we just presented for this formula. So this has a true relative error of 0.88%. So in this case, the true error is very much lower, even in the first iteration. In the second iteration, now we determine that f of xr at 14.309 and f of xl times f of xl, which is 12, which was 6.11, and then f of xr was minus. So therefore, the new xl and xu will be between 12 and 14.309. Okay, so between 12 and 14.309. Yeah, here there is a typing error. It should be 14.309, not 9309. So 9 is actually extra over here. Okay, so for this, then we determine 14.309 minus, it should be not 14.9309, it should be 14.309 minus and 0.25, which is the upper bound function value, minus the times the xl minus xu divided by f of xl minus f of xu is equal to 14.8151. Okay, yeah, you can check the calculations over here. I think there is some mistyping somewhere in these calculations, but anyway, the answers are accurate. So from 14.309, our next approximation is now 14.8151. So which has a true relative error of 0.09 and the approximate relative error of 0.78%. So additional iterations can be performed to refine the estimate of the root. So bisection versus the false position method. Okay, in the bisection and the false position method, the difference is that for the true percentage relative error in the false position method continuously decreases, whereas in the bisection method there is kind of like a zigzag situation, but ultimately the true percentage error also decreases. And you can also see that the true percentage error decreases very relatively quite faster for most of these situations. Okay, however, you cannot generalize it for every function. So this we can see in this example. Okay, so using the bisection and the false position to locate the root of f of x is equal to x power 10 minus 1 between x is equal to 0 and 1.3. So for this special function, you will see that the false position method does not provide you very quick results. So by the same approach as we can see, as we have seen in the Microsoft Excel, we can apply the false position method, and then we can see that after the fifth iteration, the solution is about 1.1015 with the percentage relative error of 4% and true percentage error of 1.6%. Okay, by the bisection method. However, when we apply this equation by the false position method, we find the XR is equal to 0.4078, which gives us a true percentage error of 59.2% and 17.1%. So this is after the fifth iteration. So you can see that after the fifth iteration in the false position method, the true percentage error is still quite high. So it means that in this case, the false position method is not giving you the good results. So this we can see with the help of this graphical representation of this function. So since this function was x to the power 10 minus 1, so initially this function for the smaller values of x does not increase very much appreciably, but only after near the values of 10, it increases appreciably. So therefore, in the false position method, we just try to linearly approximate, but that linear approximation is not very accurate in this situation. And then in this case, by these repeated efforts, we can come closer to that, but it will require more number of iterations. So in this case, generally, as we can see that the false position method is faster than the bisection method, but in this case, and like some other cases in which the function does not vary very much near the solution, then we can see that the method, the false position method, may not give you the quicker results compared with the bisection method. Okay, so the convergence of the false position method in this case is not better than the bisection method. Okay, so that's all for this topic. Maybe I could explain false position method more by performing some calculations on the Excel, but I think the time is finished. But I would recommend you to try these calculations, for example, for the one shown on this tabular format on Excel, and then this will give you more confidence in your solution, way of solutions.
I have
Okay,
a
that's
question.
all. So, do you have any question?
Yes. So can we generalize the rule for the false position method that if the, let's say, the functions, like the slope of the function, like grows rapidly, as it was shown in the last like 5.6 example, there is like exponential growth of the
Yes.
house. Then the false position method, the usage of false position method is not like likely to be used.
Yes. So for the false position method, for this kind of function where the slope is gradually increasing, okay, then the false position method will give you the good results. But for this type of solution, when initially the slope is like quite very flat and then it increases very rapidly, then the false position method will not give you the good result. You are correct.
Okay, thank you.
Yeah, any more questions?
No questions.